Hello and welcome to this next video tutorial. In this tutorial, we'll be learning about suborbitals. Now, you may have learned about many cells in previous classes. So, you may know about K cell, L cell, M cell, and N cell. Now, you may also know that K cell holds up to 2 electrons, L cell holds up to 8 electrons, and N cell holds up to 8 electrons. This helps, and N cell holds up to 2 electrons for first 20 elements. You may also have studied that beyond the first 20 elements, it follows 2n square rule, where n equals to number of cell. Which cell it is? That is, if n equals to 1, then we'll have 2 electrons in first cell. If n equals to 2, we'll have 2 squared equals to 4 into 2 equals to 8 electrons, and so on. Now, what we'll be learning in this chapter is not about cell but about suborbitals, that is SPD suborbitals. Now, what you need to know here is that each suborbitals Now, what you need to know is there are basically 4 types of suborbitals. They are S, P, D, and F. But we will not be learning about F in this chapter. So our primary focus will be on SPD suborbitals. SPD orbitals. Now, let us consider first 4 elements: hydrogen, helium, lithium, and beryllium. Hydrogen, helium, lithium, beryllium. As you all know that hydrogen has 1 electron, helium has 2 electrons, lithium has 3 electrons, and beryllium has 4 electrons. You may also choose to write it as 1, and helium is 2, and lithium is 2, 1, and beryllium is 2, 2. As we have learned earlier that first cell holds up to only 2 electrons, and after that the electrons are filled in the next orbital, so 2, 1, 2, 2, and so on up to neon, which has 10 electrons to 8. Now, when you approach sodium, sodium has 11 electrons, which means 2, 8, 1, because the second cell cannot hold up more than 8 electrons, so the next electron will be placed in M cell. Oh, sorry, yes, M cell. So this is K cell, this is L cell, this is M cell. Now, the concept of cell is not very clear, so there is a new way of studying all these. These are called orbitals. So, what we need to know is, first of all, where the orbitals lie. The concept of orbital is not a complete case too, because orbitals naturally do not exist. They are just a region around the nucleus in which the probability of finding electron is higher. Okay, I'll write it down. First of all, S orbital is filled and P is filled and D is filled and F is filled. So this means P has higher energy than S, D has higher energy than P, and F has higher energy than F. Energy level is increasing. Energy level is increasing. Now let's begin. For hydrogen, it was 1s1. For helium, helium 2. Helium has 2 electrons, so 1s2. Now, lithium. Now, as you remember, the first cell can only accommodate 2 electrons, So lithium has 3 electrons. This means now we will be shifting our case to the next cell. Hence, we'll write 1s2, and now we are shifting to the next cell. So our principal quantum number will be 2, and we'll begin starting with s, 2s1, because we know that electrons will be filled from orbitals with lower energy to higher energy, and s has lower energy compared to other orbitals. Now beryllium has 4 electrons, so 1s2, 2s2. Now boron. For boron has 5 electrons, so 1s2. Now we know that s orbitals can accommodate up to only 2 electrons, but the second orbital can accommodate up to 6 electrons. So we will not be shifting the principal quantum number. We are still in principal quantum number 2, but we will be shifting our orbital p1. Now carbon, for carbon 1s2, 2s2, 2p2, because it has 6 electrons. Nitrogen 1s2, 2s2, 2p3. Oxygen, for oxygen it's 1s2, 2s2, 2p4. Fluorine 1s2, 2s2, 2p5. For neon 1s2, 2s2, 2p6. Now for sodium, we know sodium has 11 electrons. Now what we also know that second principal quantum number, that is second cell, can have up to just 8 electrons. Now which is completed, 6 plus 2 equals to 8. So for the 11th electron of sodium, we will be now shifting to the third principal quantum number. So sodium is written as 1s2, 2s2, 2p6, and 3s1. And for magnesium, now there is a slight different way of writing the electron configuration of higher elements, because it gets too lengthy to write down the entire electron configuration. Hence, we denote the electron configuration of noble gas in the beginning, because now for sodium this pattern continues. Hence, we'll write Ne, neon, which denotes neon, because neon is the noble gas, and we'll write 3s2 for aluminium. Now the s orbital can accommodate up to just 2 electrons, so now we'll be shifting to the p orbitals, sp1 till argon, which is Ne, 3s2, 3p6 with 18 electrons. Now for potassium, we are still under the first 20 elements. So potassium has 19 electrons. Now since argon is the closest noble gas to potassium, so we'll be denoting the electron configuration of potassium like this: argon, and we'll be adding the next electron in the fourth principal quantum number, because we know that for the first 20 electrons, the third orbital can accommodate up to just 8 electrons. 6 plus 2, 8. So now we'll be shifting to the fourth quantum number, OS1, and calcium gets OS2. Now, although they may seem pretty difficult, they are not just, they are very simple. A few practices and you will be perfect in this case. Now, what will happen if we move from the 20th electron beyond? That is, what will happen if we go from the 21st element to the 30th element? So, let's do that too. The 21st element is scandium, that is Sc. Now, as I have told you earlier, the 288 rule just applies for the first 20 electrons, first 20 elements, but according to 2n square rule, when n equals to 3, the orbital can accommodate up to 2 into 3 squared, that is 18 electrons. So, let me write the little configuration of calcium over there. Calcium is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. But what you know is beyond the 20th element, that is 21st to beyond, the third orbital can accommodate up to 18 electrons. So now we'll be going back to the third principal quantum number. So for scandium it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, and 4s2. That is 3d1 and 4s2. So now titanium 1s2, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. Vanadium 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, and 4s2. Chromium. Now, I'll be noting this is argon because it's too lengthy to write the entire configuration, as argon is 1s2, 2s2, 2p6, 3s2, and 3p6 argon. And for chromium, we'll see a bit of anomaly and 3s1. Now we'll be learning about this in detail after I write the entire configuration of the first 30 elements. Now chromium is a bit different. Manganese, now it comes back to the normal pattern, that is 3D. Oh, sorry, that is 3d5. 3d5 and 4s2 either. Cobalt, that is a capital C and small o. If you write capital C and capital O, that denotes carbon monoxide. So please be careful of denoting cobalt. It is capital C and small o. Nickel, for nickel is argon 3d8, 4s2, and copper. Now, in case of copper, you will see a small anomaly, 4s1. Now, if you pay close attention, you may be able to see a pattern over here. If not, I'll teach you later. And finally, zinc, argon 3d10 and 4s2. So These are the electron configuration of the element number 20 to 30 from calcium to G. Now, we'll see a small change in the pattern in the electron configuration of chromium and copper. Now, why is this happening over here? To learn about this, we'll have to learn in detail about the suborbitals of sp and d orbitals. So, let's do that. Now, as I have told you earlier, each suborbital can accommodate up to just 2 electrons, and since S has no suborbitals, so we'll be denoting S as this. Now, we'll be learning electron configuration in box and arrow form. S is this, and P, since P has 3 suborbitals, so we'll be denoting P using 3 boxes. The first one is Px, the second one is Py, and the last one is Pz. And D is this one. The first one dx, dy, dz, dx square minus y square minus, and the last one dz square. So now what we need to know here is that the electrons are first filled singly in each of the suborbitals. That is, first of all, the electron is filled in this way. I am denoting electron with the arrow. Now, the 2 electrons in each of the suborbitals are the electrons with opposite spins. That is, they repel each other, so they have opposite spins. Now, first the electron is filled in this way, the s orbitals. Now, when the s orbital is filled, we'll be moving to the p orbital, and in p orbital, first of all, electron with same spin are filled. So it is filled in this way, not in this way, not in this way. Electrons are first filled singly, and the fourth electron will be filled over here with the opposite spin. And for D, same is the case. First electrons are filled in the empty orbitals, and once they are filled, the electrons pair. Now, as I have told you, electrons repel. So, due to the repulsion, there was the anomaly in chromium and copper. Now, what you also need to learn here is that fully filled and half-filled orbitals are stable. Fully filled and half-filled orbitals are stable. So, now, this may make a little sense to you after you learn this case. So, the reason for the anomaly in copper and chromium is entirely based on this theorem. I'd say fully filled and half-filled orbitals are stable. So let me write down the configuration of our projected electron configuration of chromium. It should have been 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. But what has happened is that one electron from the s orbital transfers to the d orbital, and all other are the same. The change is seen in just these 2 orbitals. So it should have been this 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. But What it really is this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5. Because we know that, wait a minute, I'll be teaching it more clearly now. Now, 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, and 4s2. If we try to follow the trend, the electrical configuration of chromium must have been this, but it is incorrect. The correct electrical configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, and 4s1, because we know that d orbital has 5 solid orbitals. So, as I have told you previously, half-filled orbitals are stable, and each of the elements tries to be in stable form. So, the one electron from 4s orbital travels from here and goes into the d orbital. Hence, both these orbitals are half-filled, which are stable. So, to attain stability, chromium shows anomaly and changes from 3d4, 4s2 to 3d5, and 4s1. So, same is the case in copper. In copper too, if it had followed the trend, the electron configuration of copper would have been argon, same is the case in copper. If it had followed the trend, the electron configuration of copper would have been this: 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, and 4s2. But this is incorrect. The correct electron configuration of copper is 1s2, 2s2, 2p6, 3s2, 3d6, 3d10, and 4s1. Because to attain stability, because we know that 3d10 is a fully filled orbital. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d and 4s is a half filled. This one is fully filled and this one is half filled. Both of these are stable. So your instability proper has changed into configuration from this one to this. So it's very simple. It's not too difficult. Now let's move on to the shape of S and P orbital. Now, I have told you earlier, the case of orbital is not very definitive because orbitals do not exist. They are just imaginary region. So, but I know that the electron in S orbital move in a spherical region. That is, electrons move around in this pattern, which forms a sphere. Basically, this is the real case. The electrons move, and while moving on, they form a spherical pattern. So, S orbital is spherical in shape. Remember to set the circle while making the orbital, because if you do not set, it is just a circular pattern. So remember to set the region. So a shaded circle is a sphere in chemistry. So make a round circle and say it. Yes. Now, what about p orbital? Now, in case of p orbital 2 is a region. So, in p orbital, the electrons are mainly found in a dumbbell shape. That is, electrons move around in this pattern. So, while moving on, they form this shape. That is dumbbell shape. And remember to set this part too. This is not big deal. These are just electrons moving around. So while the electrons move, they form a dumbbell shape. I'll make a basic shape. See the dumbbell shape, and do not forget to save it. So now, what does Px, Py, and Pz mean? So we know that the electrons move in three dimensions, that is in length, breadth, and height. So Px, Py, and Pz basically means the three dimensions. Let this be x and y region, and this be z region. So Px means the dumbbell shape in x-axis. This is Px, and for Py the dumbbell is in y-axis. Py and Pz it is the dumbbell in z-axis. Pz. So it is not a big deal. These are just the shapes of the suborbitals. Now, what we have learned till now is the electron configuration of atoms. Now, what about the electron configuration of ions? Now, for ions, it is just the same. You calculate the number of electrons and write the electron configuration. That is, for oxygen ion, we know that oxygen atom has 8 electrons, and since it has 2 negative charge, the ion has 2 charges, that means it has gained 2 more electrons, that's 10 electrons. So now write the electron configuration of the atom which has 10 electrons, which is 1s2, 2s2, 2p6. It is same as the electron configuration of neon atom. So it is not a big deal, just calculate the number of electrons and write it down. But again, there is a little bit of anomaly in this case too. These are in the elements between 21 to 30. Now, as I have told you, electrons are filled from orbitals with lower energy to higher energy, and the principal quantum number also has energy, that is 2 has greater energy than 1, 2 has greater energy than 2. So basically, S has lower energy than P, P has lower energy than D, and D has lower energy than F. Now, same is the case in principal quantum number, that is 1s has lower energy than 2s, 2s has lower energy than 3s, 4s. Same is the case in p orbitals too. 1p has less energy than 2p, 2p has less energy than 3p, and 3p has less energy than 4p. Now, what we have noticed is that in case of scandium, we know that 3s has lower energy than 3p, and 4s has higher energy than 3p. But In case of transition elements, why is the electron first filled in s orbital and then in p orbital? So now we look at this. According to the pattern, 1s has the lowest energy, then 2s, then 2p, then 3s, then 3p, then 3d, then 4s. This must have been the pattern, but again, chemistry is full of anomalies. Now, the anomaly source seen in this case is this: 1s, 2s, 2p, 3s, 3p, 4s, and 3d, which means 4s is lower energy than 3d, and hence the electron is first filled in 4s orbital, then in 3d orbital. That is why, in case of scandium 2 zinc, the electrons are first filled in d orbital and then in s orbital. Oh, sorry, first in s orbital, then in d orbital. Let me write an electron configuration of any atom. Manganese, one s 2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d5. So first of all, the electron is filled in s orbital and then in d orbital. Now, in case of iron, when electrons are loosed, that is, in case of positive ion, when an atom loses electron to be a positive ion, electrons are first loosed from orbitals with higher energy and then to lower energy. That is just vice versa. That is, in case of filling, the electrons are filled from lower orbital to higher orbital, and in case of removal of electrons are first removed from orbitals with higher energy, then goes down to the orbitals with lower energy. But now let me write the electron configuration of iron. The the atomic number of iron is 26. That is, the electron configuration of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Now, what will be the electron configuration of Fe2 plus ions? Now, according to the trend I just told you, it should have been 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d4. But this doesn't happen. As I told you, chemistry is full of anomalous points, anomalous regions. So, now, why does this not happen? Because now, a very important thing you need to know here is, before filling of electron, 4s has lower energy compared to 3d. But when electron is filled, the energy level changes. Now, when the electron is filled, 4s will have higher energy compared to 3d. Let me write it down.